We're here to unpack a whole stack of sources and really bring you the most important, insightful, and sometimes pretty surprising nuggets of knowledge.
That's the plan.
And today we are diving deep into something that, well, it quite literally shapes every single moment of your day, even if you never consciously think about it.
Yeah.
The world of engineering.
I know.
I mean, seriously, just think about the air you're breathing indoors right now,
Right.
or the device you're listening on, the clean water you had this morning. An engineer, or probably a whole team of them, had a hand in almost all of it.
It's actually kind of amazing when you stop and consider it, how completely foundational this profession is to, well, everything modern. They really are the unseen architects.
Unseen architects, I like that.
Yeah, just tirelessly working behind the scenes, making our lives not just possible, but comfortable, efficient, and always pushing for innovation.
Absolutely. So our mission today is to really unpack the reality of engineering, its massive daily impact, the key traits that make engineers tick, the huge societal challenges they're actually tackling,
Right.
and the incredibly diverse career paths you can take within this field. We're basing this exploration on Engineering Fundamentals Chapter 1, which is a really solid text. It gives a comprehensive look at what engineers do, why it matters, and how you become one.
So get ready to discover these often invisible architects shaping our world.
Let's do it. So to really get a feel for just how, well, everywhere engineering is, let's try a little thought experiment.
Okay, I'm listening.
Picture tomorrow morning, the very moment you wake up.
All right. Still in bed? Maybe hitting snooze.
Maybe. But notice the room temperature. It's probably just right.
Hopefully.
That perfect temperature, that's mechanical engineers. They're the ones designing the heating, ventilation, and air conditioning, the HVAC systems.
Keeps us comfortable, for sure.
Yeah.
And then, say, you reach over, flip on the lights, or maybe turn on the TV for the morning news.
Yeah.
You're instantly plugging into this vast network. There are thousands of mechanical and electrical engineers working behind the scenes.
From the power plants.
Exactly. Generating the electricity all the way to the grid that keeps that flow constant and reliable. And the TV itself. That's electrical and electronic engineers, plus manufacturing and industrial engineers figuring out how to build it efficiently.
Wow. So, okay, before I've even managed to get out of bed, engineers have basically orchestrated this whole comfort and convenience symphony around me.
Pretty much.
What about getting ready? The shower, clean water coming out the tap?
Yes.
Yes.
That's civil engineers making sure the water supply system works, and mechanical engineers might be involved too, even if you're out in the country with a well.
Right.
That well pump, designed by mechanical and civil engineers.
And heating the water, if it's natural gas.
Oh yeah, then you're bringing in chemical, mechanical, civil, and petroleum engineers. There's a whole chain.
It makes you wonder if engineers ever just walk into a room and feel overwhelmed by seeing all their work everywhere.
It's almost alarming how much thought goes into stuff we just use without a second thought, isn't it?
It really is.
And if you connect that to the bigger picture, it just highlights the deep, multidisciplinary nature of it all. Think about your towel or the clothes you put on.
Okay, cotton towel.
Right. That involves agricultural engineers for growing the cotton. Then industrial and manufacturing engineers for the machines that process it.
Huh.
Chemical and petroleum engineers for dyes, or if it's polyester, for the synthetic fibers, and even civil and mechanical engineers dealing with the factory itself, the sewing machines. Every single step is engineered.
And breakfast. Okay, the milk in the fridge.
The refrigerator itself. Mechanical engineers designing the components, chemical engineers looking into, say, alternative refrigerant fluids that are better for the environment, electrical engineers designing the controls, the power units.
And then getting to work or school. The car, the bus.
Oh, that's a massive collaboration right there.
Yeah.
Automotive engineers, obviously, but also mechanical for the engine, electrical and electronic for all the systems.
Yeah, cars are packed with electronics now.
Totally. Materials engineers working on lighter, stronger frames, even chemical and petroleum engineers dealing with the fuels, the lubricants. It's like this huge unseen ballet.
That's a great way to put it, an unseen ballet.
What's really remarkable, I think, isn't just that engineers are involved in everything. It's how they've systematically designed our lives to be so, well, effortlessly comfortable and reliable.
We really do take it for granted.
We absolutely do. We rarely stop to think about the sheer number of problems solved or potential failures avoided, the layers of expertise that go into just a simple light switch or a clean glass of water.
Yeah.
That invisible reliability, that sort of constant, silent problem solving, that in itself is a huge engineering achievement.
It really does change how you look at the world around you. Okay, so if that's the kind of impact engineers have, what kind of person actually does this? What's at the core of being an engineer? What defines them?
Well, at their absolute core, engineers are problem solvers, relentless ones.
Okay.
They're kind of like master chefs who deeply understand the ingredients, in this case, the fundamental laws of physics and chemistry. And then they use the precise measurements of mathematics to create everything from, your phone to a massive bridge.
So it's not just building, it's inventing solutions.
Exactly. And when they design something, it's not just about making it work. They're constantly thinking about sustainability, efficiency, cost, reliability, and crucially, safety.
Safety seems paramount.
Yeah, absolutely. And, a true engineer is also dedicated to lifelong learning and fundamentally service to others.
You mentioned lifelong learning there. That seems critical today. Things change so fast. But what does that actually look like for an engineer day to day? Is it just keeping up with software, or is it deeper?
That's a great question. The research really emphasizes that in today's incredibly fast-paced tech world, continuous learning isn't just like a nice bonus. It's absolutely vital.
Right.
Think seminars, workshops, reading new research papers. It's all essential for engineers to stay sharp, to stay relevant. If you don't, you honestly risk career stagnation.
Makes sense.
And this constant learning also fuels their versatility. That strong core knowledge lets engineers move between related fields sometimes. Like a mechanical engineer might end up working in aerospace or automotive or even chemical engineering roles. It's about adapting.
That adaptability sounds powerful. What other traits are really essential? It can't just be about liking to build stuff or take things apart, right?
Definitely not. You're spot on. Beyond the technical aptitude, good engineers are analytical, incredibly detail-oriented.
The details matter.
Hugely. And creative. That's maybe something people don't always connect with engineering, but it's crucial for finding new solutions. And they need strong communication skills.
Yeah.
Both written and oral. This is so important for working with colleagues, clients, even sales and marketing teams.
Right. Explaining complex ideas simply.
Exactly. Their reports might be these long technical documents full of graphs and charts, or they might just be a brief critical memo. Needs clarity either way.
And I imagine, given how complex everything is, they're rarely working totally alone.
Almost never. Engineers typically work in teams. You have to break down these massive, complex problems into smaller, manageable tasks.
Divide and conquer.
Precisely. And in today's global market, strong interpersonal skills are just non-negotiable. You need that cooperation, that coordination. Think about car parts again. They might come from different companies to different countries.
Wow, yeah.
Engineers need to make sure all those pieces fit and work together perfectly. And of course, they need to be technologically proficient, really good with computers for modeling, analyzing problems.
Makes sense.
And finally, active participation in professional organizations, going to seminars, workshops, maybe presenting their own work. That's really a hallmark of a successful, engaged engineer.
So it's clearly a demanding field, hugely impactful, but it's not just about making our daily lives smoother or building cool stuff. Engineers are really on the front lines, aren't they? Grappling with some of the biggest challenges humanity is facing.
They absolutely are, which raises a huge question. How do we sustain a rapidly growing population on a planet with, well, finite resources?
Yeah, the numbers are staggering.
They really are. The world population jumped from about 1 billion at the start of the 19th century to 6 billion at the start of the 20th, and projections suggest maybe 9.3 billion by 2050. That's a lot of people.
Which leads right into this idea of the sustainability imperative, doesn't it?
Exactly. There was a UN report back in 2005, the Millennium Ecosystem Assessment Synthesis Report. And it basically said the world was already using about 20% more resources than the planet could sustainably provide.
Wow, even back then.
Even back then. So engineers are absolutely central to bridging that gap. They're the ones who have to innovate, create new goods and services that raise living standards, advance healthcare, but do it all while seriously addressing environmental and sustainability concerns.
Doing more with less, maybe? Or just doing things totally differently?
Both, probably. And it's not just the sheer number of people, it's the changing demographics too, right? Like the aging population.
That's a big one.
Huge. The world's elderly population, folks 65 and older, is projected to more than double in the next 25 years. That creates completely new needs, new demands for engineered solutions. Think sophisticated medical devices, more accessible homes and cities.
Yeah, a whole range of things.
And then there's just the dynamic economy itself. Rapid changes, new technologies popping up all the time. That creates new jobs, sure. but it also eliminates others.
So it really sounds like a field with massive future demand.
It is. And the data backs that up. The U.S. Bureau of Labor Statistics consistently identifies engineers, along with computer specialists and systems analysts, as being among the fastest growing occupations. So this really serves as a powerful call to action, I think, for anyone considering this path. Future engineers are going to play an absolutely vital role, raising global living standards, tackling these huge environmental and population challenges. It affects every single one of us.
Okay, so we've covered what engineers do, why they're so crucial globally, their core traits. Now, let's get into the sheer variety within the field itself. You hear engineer, but that covers a lot. How many different types are there, really?
Well, there are actually over 20 major disciplines that are officially recognized by professional societies. And then within each of those, you find even more specializations.
Like branches on a tree.
Exactly. So mechanical engineering might split into, say, thermal fluid systems versus structural solid systems. Civil engineering branches into environmental, geotechnical, water resources, transportation, structural. It's a really vast landscape.
Let's start with some of the big ones, the sort of parent disciplines, maybe. Civil engineering, you mentioned, that's probably the oldest. Building the foundations of society.
That's right. Civil engineers are really the backbone of our public infrastructure. They design and supervise the construction of, well, pretty much everything you see around you that's built. Buildings, roads, bridges, dams, tunnels, mass transit systems, airports.
Water and sewage systems, too.
Yep, municipal water and sewage systems as well. The job outlook for civil engineers tends to stay pretty good, mainly because of population growth and just the constant need for new infrastructure and, crucially, maintaining what we already have.
Okay. Then there's electrical and electronic engineering. You called it the nervous system earlier.
Yeah, I think that fits. It's currently the largest single discipline. So electrical engineers typically design the bigger equipment, lighting systems, building wiring, power generation equipment, motors, control devices, radar systems.
Got it. And electronic.
Electronic engineers focus more on the smaller, intricate components in computer hardware, networks, communication devices like your cell phone, TVs, audio, video equipment, all that stuff.
That's about look there. Still strong.
Yeah, consistently good. It's constantly fueled by our, let's be honest, insatiable demand for faster computers, better communication, more connected devices.
That makes sense. Okay, what about mechanical engineering? You said it's one of the broadest.
It really is. Mechanical engineers design all sorts of things. Machines, robots, tools, power generating equipment like turbines.
HVAC systems you mentioned earlier?
Right, HVAC systems, internal combustion engines. Yeah. It's a huge range. Their job outlook is also generally good, driven by demand for more efficient machines, new manufacturing processes, and especially now, alternative energy solutions.
Okay, so those are maybe the big three foundational ones, but you mentioned newer specialized fields are growing fast too, like biomedical engineering.
Oh, absolutely. Biomedical is a fascinating one. It's newer and growing incredibly fast. It really merges biology, chemistry, medicine, and engineering.
So what do they actually design?
Things like artificial limbs, artificial organs, advanced medical imaging systems, MRIs, CT scanners, and really precise devices used in medical procedures.
Wow.
And because there's such a focus on health, plus that aging population we talked about, the job outlook is considered very good. Areas like computer-assisted surgery and tissue engineering are just exploding.
And with all the focus on the environment, environmental engineers must be crucial too.
Definitely. Environmental engineering is another field that's grown a lot. It's entirely focused on solving environmental problems.
Such as?
Things like water and air pollution control, dealing with hazardous waste, figuring out safe disposal methods, improving recycling processes. They also have a very good job outlook, although it's worth noting that their employment can sometimes be a bit sensitive to shifts in political policy or government regulations.
Oh, okay. What about materials engineers? Are they the ones making stuff stronger, lighter, better?
Exactly. You can think of them as kind of modern-day alchemists. They research, develop, and meticulously test new materials, metal alloys, ceramics, plastics, composites, trying to achieve specific properties.
Like for a tennis racket?
Perfect example. Lighter, stronger materials for a tennis racket. Or, thinking bigger, the heat-resistant tiles that protected the space shuttle.
Right. That makes sense. Job prospects.
Generally good. Partly because historically there haven't been as many graduates specializing purely in material science and engineering.
Okay. And petroleum engineers with global energy needs?
Still very critical. Petroleum engineers specialize in finding and producing oil and natural gas. They work really closely with geologists to figure out the best ways to drill, how to maximize recovery from reservoirs.
And their job market, is it stable?
Employment opportunities are usually pretty favorable, again, partly due to relatively low numbers of graduates compared to demand. But it is closely tied to global oil and gas prices, so it can be cyclical.
I see.
And there are often significant opportunities for U.S.-trained petroleum engineers to work overseas.
Right. Okay, one more. Nuclear engineering. Sounds very specialized.
It is quite specialized. Nuclear engineers design, develop, monitor, and operate nuclear power equipment. That could be for generating electricity or for powering Navy ships and submarines.
What else?
They're also involved across the whole nuclear fuel cycle production, handling safe long-term waste disposal. And they even work on medical equipment that uses radiation.
Huh. And the job outlook?
Actually not bad. Again, mainly because there are relatively few graduates in this specific field. Steady opportunities tend to exist in national defense, the energy sector, and nuclear waste management.
That's an incredible range, just amazing diversity within engineering. So let's talk about actually becoming an engineer. What does that path look like, typically?
Well, the starting point for almost all entry-level engineering jobs is a bachelor's degree in engineering. That's the foundation.
And the career prospects look good, salary-wise.
Generally, yes. Now, the specific figures in our source text are from 2009, but they showed a clear trend that's largely continued. Starting salaries for engineers were significantly higher than many other fields right out of college.
Can you give an example?
Sure. Back then, chemical engineers averaged around $64,900, civil engineers about $52,000, mechanical engineers around $58,700 right at the start. That strong earning potential is still a hallmark of the profession.
And the job growth.
The U.S. Bureau of Labor Statistics consistently points to engineering fields as being among the faster-growing occupations. So the demand seems sustained.
And engineers don't only do design work, right? It sounds like they end up in lots of different roles.
Oh, absolutely. It's incredibly diverse. Many engineers go into sales roles, especially for complex technical products where that expertise is vital, or technical support, troubleshooting.
Government work, too.
Definitely. A significant number work for federal, state, and local governments. Think agencies like NASA, the Department of Defense, Department of Energy, Department of Transportation. Lots of engineers there. It's a field with really broad applications.
So if someone decides, okay, I want to do this, what's the actual academic journey like? And how do you make sure you pick a good program?
That's where accreditation becomes really important. Specifically, ABET, the Accreditation Board for Engineering and Technology.
ABET. Okay.
ABET is basically the gold standard for engineering education in the U.S. and respected worldwide. They rigorously evaluate engineering programs. They look at everything: the faculty's qualifications, the curriculum, the labs and facilities, even the admissions standards.
So checking for ABET accreditation is key.
Absolutely. It's a crucial quality check. ABET also sets out specific outcomes that students graduating from an accredited program should achieve.
Like what?
Things like being able to apply knowledge of math, science, and engineering fundamentals, designing and conducting experiments, being able to work effectively on multidisciplinary teams, understanding professional and ethical responsibilities, and back to our earlier point, recognizing the need for and being able to engage in lifelong learning.
That provides a good framework. So typically a 4-year degree, though you said many take 5. What's the coursework like?
Right. The first 2 years are often called pre-engineering. They focus on building that broad, solid foundation. Lots of math, calculus, differential equations, physics, chemistry, English, introductory engineering courses, computer science, plus humanities and social sciences for well-roundedness.
And then the last 2 years.
That's when you really dive deep into your chosen branch. The coursework becomes much more concentrated and specialized. So a mechanical engineering student will be hitting thermodynamics, fluid mechanics, machine design hard. A civil engineer might focus on structural analysis, transportation systems, geotechnical engineering, and many programs offer really great cooperative education options, or co-ops.
Where you work for a company.
Exactly. You might take a semester or 2 off from classes to work full-time for an engineering company. It gives you invaluable hands-on experience, industry contacts, and a real taste of the job before you even graduate.
That sounds incredibly useful. Now, for some engineers, especially those whose work directly impacts public safety, there's another step, right? The PE license.
Yes, the professional engineer, or PE license. This is a big deal. It's legally required in all 50 states and D.C. if an engineer's work could potentially affect public health, safety, and welfare. Think designing bridges, buildings, power systems.
So how do you get that?
It's a multi-step process. First, you need that degree from an ABET-accredited program. Then typically during your senior year or shortly after graduating, you need to pass the Fundamentals of Engineering exam, the FE exam.
Okay.
After passing the FE, you need to gain about 4 years of progressive, relevant engineer work experience under the supervision of a licensed PE. And finally, you have to pass the Principles and Practice of Engineering exam, the PE exam, which is specific to your engineering discipline.
Wow, that's quite a commitment. Which engineers usually pursue this?
It's most common and often required for civil, mechanical, chemical, and electrical engineers, especially those working in consulting or construction where they're signing off on plans. It really signifies a high level of competence and commitment to professional standards and public trust.
Okay, one last important clarification. Sometimes people hear engineering technology and might confuse it with engineering. What's the key difference there?
That's a really vital distinction to understand. Engineering technology programs are generally more hands-on, more focused on the application of existing engineering principles and technologies.
Less theory, more practice.
Kind of. There's less emphasis on the deep theoretical development and advanced mathematics you see in a traditional engineering curriculum. Engineering tech programs usually go up through integral and differential calculus, but maybe not as much beyond that, and the focus is very practical.
So what do engineering technologists typically do?
They often work alongside engineers, assisting in more application-oriented tasks. Things like manufacturing processes, construction supervision, product testing, quality control, inspection, collecting data for engineers to analyze.
Are their programs accredited?
Yes, engineering technology programs can also be accredited by ABET under different criteria. However, it's important to know that pathways to graduate studies in engineering or becoming a licensed PE might be more limited or require additional coursework for someone with an engineering technology degree compared to a traditional engineering degree. It's really about a different, though equally valuable, focus within the broader technical field.
This deep dive has really opened my eyes to the sheer scale and importance of engineering. We've seen just how profound and often invisible their impact is on our daily lives. Everything from the comfort of our homes to the vast global infrastructure connecting us all.
Yeah, and we've unpacked their core identity, haven't we? As these relentless problem solvers, these innovators, really driven by critical thinking, deep technical knowledge, but also creativity and, importantly, teamwork and a commitment to keep learning.
And we really highlighted their crucial role now and in the future in tackling some of humanity's absolute biggest challenges, population growth, the aging demographic shift, the urgent need for sustainability, navigating this incredibly dynamic global economy.
Absolutely. And the pathways into an engineering career, while structured with things like accreditation and licensure, are incredibly diverse. There are just so many different fields, so many opportunities to innovate and make a real impact on the world.
So thinking about all this, what does it mean for you, our listener? If engineers are the architects designing our present, constantly improving things, constantly adapting, what new marvels, things we might take for granted someday, will they create to address challenges we haven't even fully conceived of yet?
And maybe, just maybe, what role might you play in helping shape that incredible future?
It's definitely a powerful thought to leave you with.